just start the recording. Okay, so 2 weeks that we come back, first 2 weeks that we come back to after Christmas, we will be doing our labs. We're doing pipe surge and water hammer. So we've started looking at surge pressures and water hammer last week, started doing calculations on those. Remember, the one thing we haven't done is we haven't looked at the elasticity of the system yet. So we will be looking at that as well after Christmas. So your lab coursework is based on pipe surge. So okay, so this is what we started looking at when we looked at the rigid water column theorem last week. You can see on here that this is a very simple pipeline. We've got flow through a pipe, so obviously you're going to have frictional losses, Darcy-Weisbach equation to give you the frictional losses. You'll have minor losses as well, where you've got the constriction of the pipe diameter and the outlet valve at the end. And when we looked at this, we talked about the fact that on the right-hand side here, obviously we've got our head, that you can just see there on the right. And if that valve is closed, we have this increase in surge pressure delta H. And last week we used the rigid column theorem to calculate that value of delta H. So just to summarize again, surge pressures, it's very difficult to remove surge pressures out of a system completely. They will occur because there will always be valves opening or closing. Obviously, if there is failure, then that's a much bigger problem because there's potential damage to machinery. But surge pressures will occur when there is some sort of change in the system dynamics. So what we have to think about is how do we accommodate those surge pressures? And last week we looked at a number of, well, a small number, because there are other ways to manage surge pressures, and one of which is the surge tower, surge tank, which is what our experiment is based on. So when we've got static flow, so this is actually a simple diagram of the kit that we're going to be using after Christmas. So I will show you exactly what that equipment looks like now, and obviously you'll see it in the lab as well. But what you'd expect in this system where there is no flow and you have a closed valve is that the reservoir level will be the same level as the surge tower. Now, depending on how that system is set up, there is going to be, you know, plus or minus, say, 10% variance in those two levels. If they aren't perfectly leveled, you know, if the ground isn't leveled, and you'll find with the kit in the laboratory that there is a slight variation. So we'd expect plus or minus, say, 10% variation within the difference between the reservoir and the surge tower, simply because it may not have been set up perfectly to allow for that level. But there is no friction, there's no movement of water, so the reservoir and the surge towers should be very, very similar. When we've got steady state conditions, so when the valve is open and we've got the flow and the movement of the water, then obviously you're going to have a drop in this level that will be the steady state head loss. So the head loss then will be equal to the reservoir level minus the steady state values in there. Okay, so we can do a simple calculation. Now, one of the things about the kit in the laboratory, unlike the laboratory equipment you've used in the past, unfortunately, as far as I'm concerned, the equipment calculates almost everything for you. So there is a bit more research analysis to this coursework, because it will actually, the software, as you'll see when we go down there, is that it does calculate a lot of the values for you. But you have to also demonstrate those values. So you've got all the formulas you need in the coursework, but you still have to demonstrate how those values are attained, even though you'll have them in your files. Okay. So the kit in the lab, when we've looked at head loss and varying head flow, we know that flow rate is not a linear relationship with head loss. So we know that there is a variation in those values, and it will vary dependent on some different power. So dependent on what sort of outlet we're looking at. If we were looking at an orifice outlet where we've got h to the power of a half, if we're looking at a weir, if we're looking at a weir, if we're looking at a large orifice, the relationship between head loss and discharge rate are not linear. So there is a set relationship. And for the piece of equipment in the laboratory, the relationship between head loss and flow rate is y equals mx to the 1.75. Okay, so obviously y is your vertical axis and x is your horizontal. So you've got head loss is equal to mq to the 1.75. So this is one of the things that you'll have to do within the laboratory, is you have to plot head loss versus flow rate and show that that exponential should be close to 1.75. And if it isn't, why isn't it? So you'll have enough information from the lab to plot that graph as a starting point. Okay, so that is specific to the equipment in the laboratory. That's the relationship when water is flowing through that system between head loss and flow rate. We're going to also look at different oscillations. So when you see the equipment working, you'll see that we can look at the surge levels. So it will record the maximum surge levels. It will record the time period, and then you can determine the decay and how long it takes for a time period between oscillations. So once the valve is closed, the surge tower will start to oscillate, and it will come to a stop very, very quickly because of friction. And what you're going to determine is what is that value for T? So how long is that oscillation? And again, the system will do this for you, but you will also back that up with the calculations that we're going to have as part of that lab session. So this is the equipment. So you can see here, have you been in the labs already? You've done a lab with me, haven't you? Yeah, so you did the friction lab because that was pre-COVID, wasn't it? Was it pre-COVID? No. It was online, wasn't it? Yeah, it was online. So you haven't been in the hydraulics labs then, have you? You've seen it, okay, right, okay. So you may have seen this equipment then. This is at the back of the laboratory. So this is the surge tower. So you can see here on the left, this is the reservoir, okay? This is the surge tower that you can see on here. And the system will allow us to do two experiments, one on surge pressures and then one on measuring water hammer. Now, on the equipment that you've looked at before, so this is the hydraulic bench. On the equipment that you looked at before, you won't have done it, but I don't know if you remember, we had to measure and determine the discharge rates by measuring the time with volume. So do you remember with that, with the friction rig, we would measure the amount of volume. So you'd look at 5 litres, for example, measure how long it takes for that to flow, and then you can work out your discharge rate. This hydraulic bench actually determines the discharge rate for you. So it gives you that value already, okay? So I'll just let this play, hopefully you can see. So this is, you can see here, that's this hydraulic bench, the surge tower. I'll show you a plan view in schematic form in a moment. You'll be using the computer to record everything. And you can see here that it will actually give you the volume flow rate in litres per second or litres per minute. So you can convert that to meters cubed per second then as well. Okay, so this will record that for you. So we can control the system the same as we did with the valve, but it will give you the volume flow rate. So we don't have to record volume and time to determine that. So there's the supply tank and pump, and you can see there the recording for the discharge rates already on there. So you'll be recording those onto the system. Reservoir level. So you'll be able to record the reservoir level. So that will be before we start the system moving, we'll take the static flow conditions. So static, no movement in the pipe, determine the reservoir level and the difference then in the surge tower. And we'll also take the surge tower level. So again, the system will record the level, and this calibration on the right-hand side will give us slightly different readings. So we need to make sure that there is minimal variance between those two values. And this is the schematic setup. So you can see here on the left that we've got the reservoir and the surge tower. It's connected to the system, and it already has the software installed that allows us to record and measure this information. And this is why it does give us quite a lot of information already, which is why there's a large percentage. I'll go through the coursework in a moment, but there's a high percentage allocated for research at the end of your coursework into surge pressures and how surge pressures can be designed out of the system, not removed, but reduced. Okay. So plan view of the system, there are a number of different pipes in here that you can see. For some of them, we are only going to be using the inlet pipe for the first experiment and the surge pipe, okay? The second experiment, we will use the water hammer pipe. So mid-experiment, we will change where we are recording information from, Okay, so we'll just move the system around a little bit, and obviously we'll be in the lab to do that. This is what the VDAS front page looks like, and I know that's maybe a little bit small, but as you can see, you're going to be putting information into this system. So you'll manually input the reservoir level. You'll manually input a number of these data points, which we will go through. So you'll input the discharge level from the hydraulic bench, and then this system will calculate everything that you need in order to determine the flow. So when you do that, as I said, you have to prove those calculations as well. You have all the calculations in the coursework descriptor, so you really are just backing up the theoretical values that the system will come out with, and then discuss the variances between the actual values. So for the first experiment, we are going to change the level so that we get 5 different steady state surge levels. So we're going to adjust the flow so that we get 5 different steady state surge levels. Okay, now we're going to try and drop them equally by each time, but that's very difficult to do because obviously we're trying to control a valve for certain surge levels. So as long as we get a similar drop each time, that's absolutely fine. We're just looking for a variance in those values. You're going to record the time period, the maximum surge, and then you're going to plot those oscillations. Okay, and again, you will have all of this data in an Excel file at the end of your session. Through the values that I will give you in the coursework, through the formulas in the coursework, you can determine the theoretical period and amplitude, and then you're going to create a number of different charts as well. So one will be head loss versus flow rate, to look to determine whether or not that exponential value is 1.75. Okay, now again, that's a theoretical value. Why is yours going to be maybe different, and discuss the variances within that. You're also going to compare actual versus theoretical for all the values that you determine. So some of those will be calculated, some of them will be directly from the system, so you can compare those. And then you're also going to create a chart of amplitude against volume, and again compare actual and theoretical, and why is there variances between them. Okay, so this is all in the coursework descriptor, and again we will go through this when we're in the laboratory as well. So what happens every time we run this experiment? So once we've set up the experiment and we've got our flow, all that will happen, and hopefully after Christmas you can all be a bit hands-on with this and control the system yourself. You can see Darren is just here closing the valve. So what happens when that valve is closed? You can see the oscillations. So can you see the variance in the oscillations there? Now, whilst we can see those oscillations, the system will also be recording the maximum and minimum. So it will plot the oscillations as they are damped, and you can see they damp quite quickly, but we're going to let them go for at least a minute when we're in the lab to let them come fully to rest. So you can see that with the surge tower itself, and you'll see it on the software. So on the software, once that valve is closed, you can see those oscillations, and that is the variance against the central point. There will be some at the front here. So I won't touch it in a minute while it's running, but can you see that sort of fluctuation just at the front? Okay, you need to think about why is that occurring? What has caused that fluctuation? Okay, so have a think about that. That'll become more obvious when we're in the lab. So not now, because you can't see the equipment and what's actually happening in the lab. It will become a lot more obvious when we're in the lab. But as that surge tower comes to a stop, so this will record. So in the past, we had an old kit where the students were jumping up and down on the surge tower trying to read the top and bottom values. Now you can imagine how much fun that was and how long that took. So now obviously this system records the values for that surge, and we will let that then come to a stop. So you're going to have a set of these oscillations for 5 different values, and you're going to look to see how they vary. So when you plot them, you need to overlay them. So their starting points all need to be the same. Okay. We will obviously have a lab workshop as well once everybody has done their labs, where we use this session to go through questions to make sure everything is clear. So water hammer, again, we've looked at water hammer. So your second part of the experiment, which is the shorter of the two, is looking at a water hammer, and that uses a different setup in the system. So there is a water hammer pipe, and in the system then a quick closing valve. So again, Part of this is to compare the amplitude of pressure with theoretical predictions. So again, you'll have theoretical values and actual values, and you will look at the variances between those. You can calculate the speed of the pressure surge along the pipe, and you're going to do that for 3 sets of readings for the same flow rate. So we're not going to do various flow rates. We're going to do the same flow rate, 3 sets of readings, and that will give us statistically a good average value so that we can see how that varies. Okay, so it'll be the same flow rate, but just 3 recordings for that. So it's a slightly different setup. So I don't know if you can, I'll zoom in on this now. So you can just see here that there are 2 points, 1 and 2, where the pressure is recorded. So just on the end here, we have a quick close valve. Once that valve is closed, the surge pressure will stop and it will bounce back to the reservoir. And then obviously it will keep bouncing. With the absence of friction, it would keep going. You remember that we did the travel of the pressure wave last week, how that varies. The recordings will come at these 2 points. So there's a measured distance between those 2 points. You know how long that distance is. You know the discharge rate, so we can calculate how fast it takes for a pressure wave to move between those 2 transducers, because you have the distance. So you will have all of this information to calculate. So just here, this is the quick release valve. So hopefully you'll be able to do this. So you can see there, it's a very quick release, okay? It is manual. So, you know, as quick as we try and make it, it is still a manual release. So that is something to bear in mind when you're writing up. And it will give you the surge pressure. Now, obviously what this is giving you is it's giving you the recording as it hits the first transducer and then as it hits the second transducer. And obviously that second one, it hits the reservoir and it bounces back to that second transducer a lot sooner, doesn't it? Which is why you've got that more compressed shape. Okay, so this is showing you the pulse as the pressure wave hits those transducers. It takes longer to get back to the first one than the second, which is why you've got the variance. So you can see very clearly which of the transducers it's hitting first and second. Okay. So these are all sorts of things that we will record and then you will discuss. Okay, so let me just show you the coursework descriptor as well. So there's a lot of information in the coursework descriptor, including all of the calculations that you need. But as I say, because this system does a lot of calculations for you, there is a bit more to the write-up. Okay, so date set obviously is the day we come back to university, so that's the 10th of January. The submission is the 18th of Feb, so that gives you 4 weeks from the time the last groups of people do their lab on the second Wednesday that we come back. Okay, so it gives you 4 weeks. Obviously, you can start writing up beforehand. The part that carries the bulk of the marks in here is about reducing surge pressures. You can start doing that as soon as you want. There's no restriction on that. It's just your data set. Each group will have their own data set. So it is your responsibility to make sure that you have the data set from your group, to make sure that you record it, okay? You will all record it on the day, and then somebody will need to bring a memory stick and make sure that you can take it from the copy. You can all bring a memory stick and take your own data set, that's absolutely fine. But as long as one of you has it and you all have the same data set for your group, okay? So the return date, 18th of March, so that's 20 working days after you submit. So it's going to be marked out of 100%. It contributes 40% to the module. Okay, so this is 40% of your module. At the moment, this isn't bonded, so you need to pass both elements. That date obviously is wrong. I will adjust that. Okay. So you can see the marking here. So first of all, presentation of report and introduction. You are final year students. You're all doing dissertations now as well. You should be ensuring that your work is well presented, that it is referenced appropriately, that it has an abstract, a contents page, because there's 10% of the marks are allocated for that, okay? And how you present to a reader is as critical as the data you're presenting, because if I can't interpret it, I can't mark it, Okay, so it's really important that you present adequately. 20% for theory, apparatus and methodology. Please don't just do a cut and paste from the coursework. Just put it into your own words. It doesn't need to be a long paragraph, just bullet points of what you did in the lab. The coursework descriptor will have more than you do in the lab. So just write up what you did in the lab as bullet points. Okay, you do not need to go into 2 pages of exactly what you did. Just a bulleted list that somebody else could follow if they wanted to do the experiment. Make sure you put theory in. A lot of people forget their theory. So you should be talking about the theory around surge pressures, around water hammer. You can use some of the mathematical equations from the coursework descriptor, but again, expand on that to put your own context into this as well. So do some research. Data presentation, analysis, and interpretation. So again, that's your results, your graphs, your theoretical calculations compared to your experimental calculations, and making sure that you have done some interpretation on them. Please don't just write friction impacted this for everything. Okay, really look into the work and make sure that you can discuss why there are variances, why is friction impacting it, where is the friction impacting it. Okay, and discussions and conclusions, and again that does include a discussion on the surge pressures and the impact of surge pressures and how they can be managed out or reduced out of a system. Okay, so not just a conclusion. It is 40% of the marks. 5 lines in a conclusion is not going to get you anywhere near 40%. Most people lose their marks on section 4 in this coursework, okay, because they just summarize the report. You should not be only summarizing a lab report at this level of a degree. You should be extending and researching and referencing, okay, so there should be a lot more in that section. So further down in the coursework, you'll see, and I will, as I said, I'll post this up and you can read it. So I've given some information on what a report should look like. So what a technical report should like, aims and objectives, background, image. Please make sure you put images in, okay? If for any reason you are not able to go into the lab, you know, none of us know what's going to happen after Christmas, then I am quite happy for you to do a copy and paste of my images, okay? If that happens and I want to know why you're not in the lab for that reason to happen, all right? But you can use it if for any reason there are images there for you to use, okay? So all of the information is on here. The procedure is on here. Again, you can please read through this before the lab because, you know, although I will do the first one for you, I want you to make sure you have a little go. You haven't had any hands-on time with the labs, well, not with the hydraulics lab at least. So it'd be really good for you to get a little bit of hands-on time in the lab itself and make sure that you have a go, which is another reason for you being in smaller groups so that you can all just make sure that, you know, you can read the surge pressures, you know what's happening in the system. So please do read this beforehand just to make sure you know the procedure, okay? It also then tells you what you need to write up. So as I said, you can see all the schematics are in here. And then exactly what you have to do. So this lower, discuss the impact surge pressures can have on a system and how they can be controlled. That is part of that 40% allocation. It is not a one-liner, okay? I will give you as much help as you need with the coursework, which means I'm a quite hard marker when it comes to coursework because, you know, I'm here if you want help. So do ask for help. We'll do labs, we'll do one of these sessions where it'll be like a workshop anyway. So please do ask for help. If you think your graphs aren't right, your data's not right, please just let me know and we can go through it. The second experiment, the water hammer one, you can see again where you are comparing amplitude of pressure and theoretical predictions within those 2 transducers and then calculating the speed of the the surge along the pipe. All right. So again, all of that is here. And further down, you can see all of the calculations. So the data for the system is here. You don't need to go searching for any of that. This is all relates directly to the kit in the laboratory. So you will need some of these. And then all of the theory calculations are all in this coursework, okay? So what I'm expecting you to do outside of the calculations is to research the theory a bit more and also that element of surge pressures, the problems with surge pressures, how to control surge pressures at the end for that 40%. So that isn't in here. So please make sure that you add that session, that bit in, to make sure you get some good marks, okay? So everything you need other than that is in this coursework, okay? Are there any questions? Now, I will put this up, and actually I'll put the PowerPoint up. So, oh no, I've talked through it, so it'll record, it's recorded. So I'll put this recording up, but as I say, the benefit this year is we will be in the lab. If that changes for any reason, then I will go down and do a full recording of the lab with you watching it, all right? If for any reason that after Christmas something changes and we cannot get in, I will do a new recording where you're watching the full experiment. But hopefully we'll be in the labs and you'll be doing it yourself, okay? But we'll make sure we plan for worst case scenario. So with a bit of luck, you'll all be in the lab and doing this. I will run for each group, I will do the first run through so you know exactly what you're doing, and then you'll record the rest of your experiments, okay? So it's not more than a 50-minute time in the lab anyway to make sure you get your data. Okay, are there any questions? Everyone online okay? Yeah, okay, good. So what I want you to do then is I will post this up this week with the risk assessment. Please just check the rota. If I've missed you for any reason, can you please let me know as soon as possible? If there is for any reason that you cannot make the assigned session, and as I say, as a full timer, that really should not be the case. But if for, you can do it the following week, if you speak to a colleague and you wish to switch groups, I'm fine with that. But I need you both to agree that with me. So I need an email from both of you if there is for any reason. But, as full-time students, you should be available every day to be on campus as necessary. With COVID, obviously, I appreciate that that is different and some people will have other restrictions. But please let me know as soon as possible if that is the case, because, the rotas are, as you can imagine, it's quite tricky to rearrange these sorts of things, and I need to do it fairly quickly to make sure everybody is getting a bit of time in the lab. Now, do you all have PPE? Were you all given PPE? You've all got that, that's fine. Okay, great. Okay, so you should have had that in your first year anyway, I think. So hopefully that's okay. So for the hydraulics lab, it's your lab coat and your shoes, okay? We're obviously working with water, but the equipment is heavy. If it falls on your toes, then that's something we don't want to happen. You don't need your goggles in the lab. Everything is a sealed system anyway, and it is only water, okay? So do make sure that you're safe, and we'll have a look at the lab. And if we've got a few minutes at the end, then we'll run the new hydraulic flume, so you can have a look at a hydraulic jump as well, because you won't have seen that in real life either. Okay, so we'll have that running in the background, hopefully. Okay, so that's all we're going to do today, last week of term. So we're not going to start anything new now, because obviously it's the lab is the key thing, really. So please go through your labs. Have a look back at your notes from last week as well, because that's the starting point for what we're doing for next week. 2 weeks of labs when we come back, and then I will, the third week, then we will do a lab workshop, make sure everybody's okay with their graphs and what they're plotting, and, so that you've already made a start on it, okay? And please do make a start on it, because you know what will happen when you come back after Christmas. You've got dissertations to think about, you'll have other assignments, so, it's going to be busy, okay? So do make a start on that. For those of you here, if I can just take a practical, it's really the end of term, isn't it? A hard copy register. Oh dear. Okay. Okay, everyone online? Yeah, see you next term, UGA. Thank you. So for those of you online, have a good Christmas, everyone. Try and enjoy it. Hopefully